Hello guys, welcome back to another tutorial. This time we're going to be looking at a beam and with some kind of loading, and we are given that due to this loading the internal stress acting on the cross section should not exceed a certain value. So we're trying to do this problem to be exact. So let's say we have a beam looking like this, and okay, here's the midspan, so L over 2 and L over 2, and right here we have a load that's gonna go something like this. So it's a distributed load, but it's triangular with a value of let's say W naught. Okay, and this support is A, and this support is B, and the midspan point is point C. And we are given that the cross section, it's an W section or I section, but we know the dimension or the dimensions of the cross section. And we are giving that sigma max is a value, and for simplicity for now let's assume that we know the let me correct this thing. Let's say that I, the moment of inertia, is given, and we want to say that the stress in the beam should be less or equal than sigma max. How can we do this symbolically? First we need to do it symbolically, then we're gonna throw out some numbers on the problem. Okay, and let's see, what do we need? So we know that sigma max, or sigma, let's say just sigma for example, it's basically the moment multiplied by some distance y that I'm going to explain, y over the moment of inertia I. This y is basically the distance, this is y, the distance between the neutral axis to the top fiber or the bottom fiber, depends on what are you trying to find. Okay, so if we're looking for in this case we have the beam, the top fiber is under compression and the bottom fiber is in tension. So if we are looking for the for example the compressive stress, that means we're going to use this y. If you're looking for the tensile stress, we're going to use this distance, which is again y. For this I-beam, if all the dimensions are symmetrical, saying that this thickness is the same as this thickness and this width is the same as this width, that basically that means that this y is equal to that y. Okay, if we're looking for the maximum stress without being concerned if the stress is compressive or tensile stress, then we need two major things. Looking at the equation, we can say that we need three things, but the two major things are the m, the moment, should be a maximum moment if we are looking for the maximum stress, and the y, if you are not concerned with the type of stress, you should pick the biggest y. That is, if this y is greater than this y, then you pick this one, and vice versa. So our goal now is to try to find the maximum moment and determine which y to use. In our case it's the same, basically the top or the bottom one, and divide this by I, given that I is a given number. Okay, so what we're trying to do now is find the maximum moment for this beam. Okay, let me try to move this just a little bit to the top, like this. Okay, alright. Now, what do we have here? This is the reaction AY, and this is BY, and I'm gonna concentrate the distributed load at the midspan, L over 2 and L over 2. The value for this load is basically the area of this triangle. So the area of this triangle is 1/2 the base. The base is basically L, and multiplied by the height, which is W naught, and that's basically W naught L over 2. Now, if this load is acting at the middle of the beam, that means this reaction and this reaction are the same, and the value for each is half of the load. So I can say AY equals BY equals 1/2 of W naught L over 2, or simply W naught L over 4. Now I'll try to take a cut at where I expect the moment to be maximum. From this loading condition, you can simply say, or you can simply see basically, that the maximum moment takes place at the midspan. Okay, so I will try to find the maximum moment in the most sufficient way at the midspan. Alright, so let's move on. Now, if I take a cross section, this is the reaction, which is W naught L over 4, and I have this load right here, and this is of course W naught, and this is L over 2. First thing first, concentrate the distributed load. This distributed load will act at certain distances that you should know by now. This one is 1/3 of L over 2, or basically L over 6, and this distance is 2/3 of L over 2, or basically L over 3. Okay, and don't forget that the moment here, the shear force goes like this, and the moment is like this. I'm gonna call this MC. Now our goal is to find MC. So the summation of the moments about C should equal to 0, and that's gonna be my positive direction. Let's sum up the moments about point C. So first I'm gonna add the MC, which is the internal moment. Then I'm gonna start from the left end. So I'm gonna have the force multiplied by the distance. The force is W naught L over 4 multiplied by the distance. The distance is L over 2. And the direction for this one is negative because it's going clockwise, which is opposite to my positive assumption. Then I'm gonna consider this force. The value for this force is basically the area of this triangle, which is 1/2 the let me do the base first here. 1/2 L over 2 multiplied by the height W naught, and that's gonna basically give me the whole thing as W naught L over 4. So the force is W naught L over 4, and the distance is this distance, which is L over 6 multiplied by L over 6, and this force, or the moment produced by this force, goes this direction, so it's a positive, and the whole thing should be equal to 0. And solving for MC, can do the math here and the simplifications. You will get W naught L square over 12. So this is my maximum moment value. Okay, now let's move on. Okay, what do we have here? Now I can go and simply apply the sigma equation, which says that sigma max equals m max multiplied by y, assuming that we know y, over I, and if I substitute W naught L square over 12 multiplied by y divided by I, simply I can say that m, or sigma max, is basically W naught L squared y divided by 12I. Now let's take a look at this equation. This equation is telling me the following. If I know the value of W naught, I know the value of the length of the beam, I know the y, which is the depth we discussed before, and I know the moment of inertia, I can plug in the numbers and come up with some stress, internal stress, which will be the maximum stress in my case, the maximum internal stress. This equation very useful if you are asked to, for example, not just to find the maximum stress. It's useful when you are given the stress. You're told that this beam cannot take more than this value of stress. What is your maximum load? Looking at this equation again, you're giving the stress, you're given I because you know the dimensions of the beam, so you can figure out the y, you know the length of the beam, you can solve for W naught and know that your beam under this load will not exceed the maximum stress allowed. Alright, let's go ahead and do a quick example. In this example I'm going to use the same beam, but this time I'm going to add some loading. I'm going to add some values here. So let's say this is half of the beam. We have these supports and we know the value here. Okay, W naught is unknown. I'm solving for W naught, okay? And I know that this thing is 12 feet and this thing is 12 feet. Alright? And I'm given the cross-section dimension. I'm not given the I yet. So I have to come up with the I, or calculate the I basically. What are the dimensions I'm given? I'm given that this thing is 8 inches. And these numbers are as follow. Let me use another color here. This thing is 10 inches. This thing is 0.3 inches. The same thing goes for this one, is 0.3 inches. And this thickness is, just for simplicity, 0.3 inches. So the question now, or your task now, is to find the I for this section. Once you have the I, and by the way, you are given that the maximum stress should not exceed 22 KSI. That's kips per square inches. And the question is, what is your W naught? Finding the I for this section is very straightforward. If you know open any engineering book concerning the mechanics of materials, you will find some equation you can use to come up with this I. But let's make sense of these equations. Of course, there is the long way. You can go ahead and you can refer to some of the tutorials I posted before, where you can basically find the centroid, and from the centroid you calculate the moment of inertia using the parallel axis theorem and all of that, all of these steps. But let's just assume again that you are doing this problem on a test and you don't have that much time. Okay, now think about it this way. This I section, or this W, I keep changing the name of the section, just bear with me. It's basically made up of two sections. One is this section minus, let's say this is my section and this is the I, minus these two. Okay, so maybe I should do it like this. This section, the original section, is made of this section minus these two rectangles. Okay, now what is the I for a rectangle section? I, moment of inertia, is bh cubed over 12. And what is the I for these two? bh cubed over 12, and this one is bh cubed over 12, and vice versa. Okay, but here's the thing. What if I said this section, or these two, can be combined into one? If I do this, here's your checkpoint. If I do this, will the centroid or will the neutral axis of this section be the same as this section? If your answer is yes, then you can say basically that the I is bh cubed over 12 for this minus bh cubed over 12 for this section. Alright, let's put some numbers here. Okay, I'll just keep this. Alright, so let's see, we have this minus, now we have another triangle here. This section is basically 8 inches, which is this 8, and multiplied by the height, which is 10 plus 0.3 and 0.3, so it's 10.6. Now for these two, this thing here, the height is 10, it's given 10 inches. For one of these rectangles, or for both, let's do them for both, it's basically the 8 and you take away this thickness. Let me use another color. So it's 8, it's this length, and you take away this thickness. So 8 minus 0.3 will give you 7.7 inches. Okay, from this one, let's go ahead here and say that I equals, what is bh cubed for this one? Bh cubed for this one is 8 multiplied by 10.6 cubed over 12 minus, for the second one, 7.7 multiplied by 10 cubed, the whole thing over 12, and if you do the math, you'll get 152.344 inches to the 4. That's the I. Okay, now we know the I, and we know the what else? We know the stress, because it's given that shouldn't exceed 22 ksi, And for this section we need the y distance. So what is the y distance? This is a very simple section. It's symmetrical about this axis. So this y is the same as this y. Okay? So it's half of the total depth. So y equals 1/2 of the total depth, which is 10.6, will give me 5.3 inches. Alright, I'm ready now to go ahead and plug in my values. Sigma equals W naught L square y divided by 12I. That's my equation. From that, if I solve for W naught, I will get 12I sigma over L square y. Alright, let's plug in the values. 12, the I is 152.344 inches to the 4, multiplied by sigma, which is 22 kips per inches square, which is KSI. The whole thing is divided by L squared, which is 24 feet. So multiply by 12 to change it into inches, and the whole thing is squared. Then y, as we said, is 5.3 inches. Now let's double check on the units. Inches squared will go like this. This thing is inches squared, of course, and this is inches cubed, so I will have inch squared multiplied by k over inch squared multiplied by inch, so I will get k by n, or kip per inch, and that's the correct unit for my distributed load. And if I plug in all these numbers, I will get the following. W naught equals 0.091 kip per inch, and I don't like this unit, so what I'm gonna do, this is kip per inch, so if I say get rid of the inch, I want foot, I say 1 foot will have 12 inches, so this inch will go with this inch. I'll end up k over ft. Then I have to multiply this number by 12, and if I do that, I will get 1.10 kip foot. Alright, now this is the load that will produce 22 KSI as an internal stress in the beam. Okay, and now you know the procedure. You can do this procedure for any beam you want. If you know how to get the equation for the maximum moment, try to plug it into the sigma equation and come up with a simplified version of this sigma equation. All you need, let's just very briefly discuss this. So we have sigma equals m max y divided by I. Now this m max is a function of W, L, and whatever. Come up with this equation as we did. We did this one, we got it W naught L square over 12. In your case, for example, for this beam with a uniform distributed load W, M equals WL squared over 8, which takes place at the midspan. So take this and plug it in here and come up with a simplified version of the stress equation. Once you do this, you will have stress on one side and you'll have W, L, Y and I on the other side. Then whatever the question asks you to find, you can find it using one of you should be able to get all of this but the unknown. So if you are asked to find W, you should have L, Y, I and sigma. If you are asked to find sigma, you should have W, L, Y, I and so on. Alright, I hope that was a useful tutorial, and I'll see you in future ones. Thank you.